Hello students. So now we will see few classical problems on synchronization. Okay. So we have three classical problems on synchronization, that is bounded buffer problem, reader and writer's problem, and dining philosopher's problem. Okay. So as I said, there is a problem called as critical section problem. So we need to find solutions to critical section problem. Okay, so any solution that you try to implement can be applied on these problems to check if the solution works perfectly fine or not. We will first see how we overcome the bounded buffer problem. Okay. Yeah. In bounded buffer problem, you know that there are two processes, right? One is a producer process and one is a consumer process. So here we have n buffers. Each buffer can hold one item. For example, I can say this is one buffer. We have three buffers, that is n is equal to 3 here, and each can hold only a single item here. Okay. Now we have three semaphores here. One is mutex, full, and empty. Mutex is initialized to 1, full is initialized to 0 because initially there are no items in the buffer, so it is 0. And what about empty? Empty is initialized to n, that is there are no items in the buffer, right? So it is completely empty. So three places are empty here. So n is also equal to 3. Full is initialized to 0 because it is not full, right? It is not full. So it is 0 and empty is n. We know that producer waits when the buffer is full. That is, if the buffer is full, then the producer cannot insert any item into the buffer. Consumer waits when the buffer is empty. That is, when the buffer is empty, consumer cannot consume from the buffer. Moving on to the next slide. Yeah. So this is the structure of producer process. Okay. So now we will see how this works. Clear? And remember, these producer and the consumer process are sharing a common, as I said, so critical section problem is nothing but it is a section wherein common things are being shared, right? So here the common thing between both the producer and consumer is buffer. They are sharing buffer. So it should so happen that they are in synchronized form, but they are not supposed to change the values in buffer such that it results in inconsistency. Okay, they should carefully modify the contents in the buffer. So let us now see the structure of producer process. Okay, so this is a infinite while condition. So let me give you an example, guys. Let us consider n equal to 3. Okay, so let us now consider as having 3 buffers. Clear? Okay, now let us go according to the code. Now this is with respect to producer, right? So producer will produce an item. Okay, so initially you I hope you know what is weight and signal. Weight is decrementing and signal is incrementing, right? So initially let us write the initial values of mutex. What do you think is initial value of mutex? It is 1. What do you think is the initial value of empty? Empty is 3, right? All the 3 are empty here. What about full? Full is initially 0, right? None of the buffers are full. So it is 0. So initially this is the status of the semaphores M. This is empty and this is full. Okay. Now let us start with it. So producer will produce an item. Let us consider that item as I1. I'll write it as 1. Okay. So initially in the first iteration, the producer weight empty. What is weight empty? Let me write here ME and F and then update its values. Okay, so weight empty. So empty is 3. So weight is going to decrement the value of 3. What does this mean, guys? See, when an item is produced, so it is supposed to be added to the buffer, right? So how many empty places are there now? 2. This is what it means. And what about full? That we will see later. Okay, that is in the signal. So you know the answer, but then that has to be done according to the code. Okay. What about mutex? Mutex should be decremented because it is a wait operation. So from 1, it is decremented to 0. Clear? Now, what happens next? This item is added into the buffer. So this item 1 is added into the buffer. So after it has been added to the buffer, you have to use 2 signals operation. One is signal mutex. It is after it is done with its job, mutex should be reset to 1. And what about signal? Signal value should be decremented. That is what signal does, right? It decrements. So from full, that is this value should be incremented. I'm sorry, this value should be incremented. You should increment signal and you should decrement weight. Okay. So signal is incremented. That is mutex is incremented from 0 to 1 and signal is incremented on full, that is from 0 to 1. So this is what it means, guys. You have 2 empty buffers and 1 full buffer. Now, second time. Okay, so the producer again produces one item. Let us name that item has to. Again, it waits empty. So what is the value of empty? Now it should be reduced, right? So 1. Then wait mutex. Mutex should be decremented to 0. Now, so the second item is added to buffer. When this item is added to buffer, you need to signal mutex. It is mutex is incremented to 1. And what about full, guys? Full was initially 1 and now it becomes 2. Likewise, you are able to see here, right? So we have only 1 empty buffer and 2 full buffer. Similarly, in the third iteration, when the producer produces an item 3, initially wait empty. So empty is going to be decremented, which is going to become 0. What about mutex? Mutex is also going to decrement. So so empty is going to be 0. That is when this 3 is added, right? So now we have 0 empty buffers. So after the item has been added to buffer, signal is mutex is signal, which is m becomes 1. And what about signal full? So full is initially 2 here in the second iteration. It now becomes 3. Okay, so this is the final status of the producer problem. That is producer. That is mutex is reset to 1. Empty is now 0 because none of the buffers are empty. That is why E is 0. And the semaphore F is 3. That is, it is completely full. Okay, so this is what is the process of producer. Now, let us think if there is a fourth item to be added. Now, when the producer tries to add this item, what happens to empty, guys? Look at the value of empty. Empty is 0. So, if you try to decrement, you get a negative value, right? You get a negative value here. If you get a negative value, you cannot add an item to buffer. You have seen in the previous cases also. If you reach down to a negative value, then you cannot enter into the critical section. This is how the fourth item is prevented to be added to buffer. That is, fourth item cannot be added to the buffer. Hence, it is prevented. Clear? The similar one, the same configuration. We will take the same configuration here. We will now take the configuration m is equal to 1, full is equal to 3, and e is equal to 0 for consumer process. Okay. Yeah. Here we have a consumer process. So this is also an infinite while condition. So this we will check for consumer. Now we will now write the same buffer here. Okay, this is buffer 1, this is buffer 2, this is buffer 3, and these are its respective items. So we saw that the values for mutex is 1 and for f it is 3. That is, we are taking from the previous one, right? And empty is equal to 0, or we can consider from here also. What is full? We have 3 places which are full and empty is going to be 0. This is the situation for consumer. So initially what happens? Okay, 1. Okay, so wait full. What happens? So you know that the consumer starts consuming the items from the buffer. So you know this is nothing but decrementing the value, and this is nothing but incrementing the value. Okay, yeah. Now, so what is it going to be? Wait full. So full is going to be reduced to 2, right? Yes. So this is going to be reduced to 2, and m value is going to be decremented to 0. That means what? One object is going to be consumed, that is 1. This is going to be consumed. So you have only two full, and once it has consumed the item, so you have to signal the mutex to 1. Okay, and what about empty, guys? Empty is going to be now 1. From 0 you have incremented, so it is going to be 1. So you can see the configuration here. You have 1 empty place here and 2 filled places. That is when item 1 is consumed. What about item 2? So when item 2 has to be consumed, so the consumer will decrement the value of full to 1. Okay, and mutex will be reduced from 1 to 0. Okay, now what happens? So this item 2 is also consumed, so full is only 1. It has only one item, that is 3 item. After it consumes, mutex is incremented from 0 to 1. What about e will be incremented from 1 to 2. So as you can see here, we have 2 empty places and only one item in the buffer. What about the third one? In the third one, to consume the third item, weight is going to be reduced. That is, full is going to be decremented from 1 to 0. And then what about the mutex? Mutex is going to be decremented from 1 to 0, right? Okay, so that is when the third item is consumed. So I can consume this third item. When this third item is consumed, you have to signal the mutex. That is, m is signaled, mutex is signaled to 1. And what about empty? Empty has to be incremented to 3. Okay, that is from 2 be incremented to 3. So you can check this configuration here also. You have how many empty buffers now? 3 empty buffers, because all the 3 are consumed, and we have 0 full buffers. Okay, so none of the buffers are having items, so it is 0 and empty is 3. This is how the consumer process is checked. Okay, so now you can think of one more consumer coming. So when the consumer comes, right, so it will check for full, right? So full is 0, and if you try to decrement 0, you get a negative value. Hence the fourth consumer cannot come into its critical section, because there are no items in the buffer to consume. This is what is a solution to bounded buffer problem, which involves producer and consumer sharing same variable. So here the shared data is buffer. Okay, thank you.